Hello everyone, my name is Enis Ceyhun ALP and this is my CMPE492 project, which is called Designing an OpenFlow-Based Dynamic Load Balancer for Data Center Networks. The project advisors are Cem Ersoy and Sinan Işık. Our motivation for this project arises from today's data center networks. Data centers host multiple servers and a front-end load balancer which directs client requests to server replicas. However, these dedicated load balancers are expensive and they become a single point of failure and congestion. This is where software-defined networking comes into play. SDN is a newly emerging paradigm which aims at separating the control plane and the data plane to improve resource utilization and to simplify the management of the networks by centralizing their controlling mechanism. So in this project, we implement a dynamic load balancing scheme for FAT3 networks using the SDN paradigm and the OpenFlow standard. The algorithm that we implement has already been proposed in the literature by Li Yu and Deng Pan. Our goal is to achieve efficient bandwidth usage and fair utilization of the resources in our network. Furthermore, we want to study the effects of timeout values of flow rules and monitoring cycle of the network statistics on the load balancing scheme. So before I continue with the details of the algorithm, I want to talk briefly about our topology. The topology that we study is called K-array FAT3 network. So the K is the network parameter value, and it determines the number of switches at each layer and also the number of host connections. So these networks consist of three layers which are called core, aggregation, and top of rack or edge layer. So depending on the location of hosts, you can see that there might be multiple paths which connect them. For example, two hosts which are in the same pod can be connected using this path or this path. Similarly, if the hosts are located in different pods, then there might be multiple paths connecting them. For example, this one and this one can be connected using this way or this way. So another observation is that if two hosts are connected to the same aggregation or core switch, this becomes the highest layer that their flow has to reach. For example, when these two hosts are connected, their flow has to reach only up to this level. One last observation is that once the highest layer is reached, there is only one way to go down to the destination host. These observations will be helpful in the future sections when we talk about the algorithm. So the algorithm is as follows. For each network flow, the algorithm establishes a path between the source and destination host. The algorithm first determines the highest layer of the tree that the flow needs to access. In order to do this, the controller uses the address information from the received packets. Then the algorithm goes upward in the tree until reaching the highest layer. Once it reaches there, the downward path to the destination is deterministic, so it doesn't have to calculate it. The algorithm builds the path recursively, and when doing this, at each switch, it checks the outgoing links. Then it chooses the link with the maximum available bandwidth. This link is also called the best fit link. Then it appends the switch that is at the other end of the link to the path. Once the path is established, this information is used to update the flow tables of the switches in that path. So the switches can forward the packets accordingly. So now the question is, how does the algorithm determine the best fit link? Since the algorithm runs on the controller, it can communicate with the switches in the network. So it monitors port statistics to make path decisions. The algorithm periodically queries the transmitted or outgoing bytes on each port from switches and determines their bandwidth usage for that monitoring cycle. Best fit link is the link with the least bandwidth usage in that last monitoring cycle. So in our project, we use different query periods to study its effects on the load balancing scheme. So in our project, we utilize different software and tools. To implement a dynamic load balancing algorithm, we utilize the Java-based float-like controller. We picked this controller because it has a nice development community, and also it has a relatively better documentation compared to other controls in the literature. Furthermore, we use Mininet for network emulation and iPerf for traffic generation in our network. So to test the algorithm, we, as I said, use Mininet, which provides default network topologies. However, it does not come with our K-array FAT3 network topology. Therefore, we prepare our own custom topology using Python and ran it on Mininet. Also, we needed constant traffic to properly test our scenarios, so we used iPerf to generate traffic. iPerf is used within the Python script to generate UDP traffic at different rates and to measure network performance. We also use different timeout values and port monitoring periods and studied their effects on load balancing. So the conclusion is, we implemented a dynamic load balancing scheme and studied its effects on resource utilization, bandwidth, and latency. Furthermore, we also studied the effects of flow rule timeout value and port monitoring period on the load balancing scheme. Finally, we familiarized ourselves with the tools for conducting SDN research such as Floodlight, Mininet, and iPerf. Thank you for your attention.